Hi, welcome and thanks for joining us. Our philosophy at BRER Technical is the foundation behind everything we do. It's why we do what we do. This video should help you better understand our philosophy so that we can prepare together and better provide for you the best possible contribution to your safety and long-term reliability.
I'm Todd Bishop, owner of BRER Technical, specialists in online testing and inspection of industrial FRP equipment. I'm here to talk about the overall strategy behind what we do, as well as some of the methods we use to accomplish the strategy. We'll go into more detail regarding the methods and tools that we use and our POISE software in other presentations. Online evaluation of FRP has been my focus for over 20 years and BRER Technical since 2000. The title of this presentation is 3 Steps to Reliable Industrial FRP. The 3 steps are: Step 1, know what the underlying condition is. It's not enough to react to visual damage. It may or may not be predictive of failure. Step 2, find the localized defects that will shut you down and fix them before they do. And Step 3, replace well. Specify thoroughly, choose a good supplier, and send knowledgeable inspection to the shop at least once during the process. Here are some of the challenges we face and the innovations that have helped us overcome them. Problem 1, information management. Many owners don't realize it, but they have over 100 separate pieces of FRP equipment that should be inspected and tracked. This is not including things like floor drains and less consequential pieces. Customers need a record of inspection, and it needs to be clear and prompt. The solution we have found is POISE, custom software that was developed in-house at BRER Technical for this purpose. It facilitates data entry in the field and assures that reporting is as clear and consistent as possible. The second problem is common test methods often don't work. FRP is irregular, non-magnetic, non-conductive, with low and variable densities. Common test methods just don't work. In short, testing used, beat up, and running FRP is a real bugger, and many of the big testing firms don't even try. One of our solutions is we've developed several proprietary methods and have especially adapted others for our use, including divot cutter, MFI, digital X-ray, thermal imaging, back when it was still nitrogen charged. And once again, we'll talk about our methods and tools in other presentations. Another problem, it degrades differently than metals. FRP often degrades on the surface like metals, but it also degrades internally, losing strength without changing thickness or visual appearance. MFI is unique and only tool that accurately determines the depth of permeation in situ, which is directly indicative of the physical strength and flexibility. Another problem, doing online right requires technology. How do you get all of your equipment to a remote location undamaged at a reasonable cost and know that you have all the supplies you need and it will set up quickly and keep secure at night? Our solution was the Mobile Materials Lab, a pop-up rapid deployment workspace. It's complete with air conditioning, heat, fully supplied and wired. It ships secure, sets up in a couple of hours, and puts our workspace down in the plant near the work. It folds down at night to secure the equipment in 15 minutes. Another problem is FRP is unique. FRP requires construction and support and safety knowledge unlike anything in metals. The solution, many of our employees have over 30 years of experience and others between 5 and 15. What does it take to create a reliable FRP system? Honestly, there are things that come before step one in the process, like identifying the equipment as a worthy PM unit and finding its place in the documentation system. We try to sketch the equipment in simple isometric to allow placement of findings. Beyond that, however, the first logical step in the process has to be the underlying technical condition of the laminate to facilitate the repair-replace decision. Robotic monitored filament insertion, or MFI, to more properly describe later, determines the exact depth of permeation from process fluids. The process of permeation is directly analogous to the loss of physical strength and flexural modulus. Robotic MFI was developed and programmed in the lab at BRER Technical. It is a practical, battery-powered system that is controlled by and deposits all data into the BRER Point of Inspection, or POIS, software system. A tiny, non-corrosive metal filament is inserted into the laminate without pre-drilling while being electrically monitored in real time. The results are graphed and the test develops, and the results displayed also in real time. In this graphic illustration, a computer running BRER software is linked to the MFI unit to insert a special metal filament. The filament is about 0.01 inches in diameter, or 10 mils, and is sealed in place by the material it displaces as it is inserted. When in place, it is either capped off or covered in a special plastic enclosure for reevaluation later. Either way, an MFI filament is never removed once inserted. Find the critical damage that will shut you down. The steps are as follows. Visually inspect with an infrared camera if appropriate. IR is a great pre-qualification tool if you have the heat. It identifies suspect areas for follow-up by other means. Battery-powered digital X-ray is fast and safer than analog and allows a cross-sectional view of the laminate from the outside while it is running. It has limitations, but can give an indication of the condition of the laminate as well. We discussed the method and limitation of this technology in the Methods and Tools presentation. Core samples are a backup position for us. They are not the first choice for inspection because of the cost and the damage they incur. We use them mainly to confirm our findings, and after the decision to replace, provide final confirmation of the decision. BRER has a proprietary fixturing to test 3-inch diameter core samples for tensile and flexural properties, and can test larger dog bone style samples as well. The following is an example of how a core sample confirmed MFI in the field. We tested an 18-inch diameter by 1-inch thick stock line and found full permeation to within almost 3/16 of an inch to the outside surface, or 0.018, even though the pipe wrapped at around 1 inch total thickness. We took a core and it looked great visually. It was 1 inch thick. The inner surface still retained the original gloss, and the veil was embedded in the original molded surface. We sectioned that core into thirds and set the corrosion barrier aside. The two structural layers were about 3/8 inch thick and were comprised of the same number of layers of matte and woven roving. We tested the two structural samples in 3-point flex and found that the inner structural layer failed at 900 pounds force, and the outer, less saturated section failed at 2,600 pounds force, about 3 times stronger. MFI predicted this degradation, and a simple core without physical testing or MFI would not have identified the problem. You need to put back equipment that meets your goals for reliability and durability. Prices are being squeezed out there, and some suppliers respond by cutting corners. It's important to define the product you want by qualified design and specification before you go out to bid, with the understanding by all involved that there will be at least some knowledgeable shop inspection to ensure that the specification is observed. Even one random inspection and a telephone pre-job will help assure that the design and specification are used. Based on our experience, if you don't provide knowledgeable shop inspection, a proper design and specification may not be worth the cost. Here's the crew at BRER Technical. We are mechanical and electronics engineers, QC professionals, test engineers, programmers, and we look forward to hearing from you and perhaps working with you in the near future. Thanks for taking the time, and we hope it has been informative.